So in this video, I'll show you how a bipolar PWM works. So the goal of a PWM for a full bridge inverter is that we have an input voltage, and then we control the switches here in order to control the output voltage. So the goal is to get the output voltage. And now the output voltage can be expressed by the input voltage and the gate signals. So we have that the output voltage, let's just call it VO, that is easier. This is equal to voltage at this point minus the voltage at this point. So we have VM1 minus VM2. Now we'll just go quickly through here. So VM1, this is equal to the input voltage multiplied with S1. Because when S1 is 1, you can see that this switch here is closed. So the voltage here is equal to the voltage here. So we get Vn, which satisfies with this equation here. And if it's 0, then we also get 0. Because then the voltage here is equal to the voltage here, which is 0. And then we can do the same for Vm2. So Vm2 equals Vn, and then multiplied by S2. So we can insert for these two equations into the output voltage. And then we get Vn, so I will just factorize out Vn. So we have S1 minus S2. So that is a very basic equation for the output voltage. Now, if you want a more detailed understanding on how the full bridge inverter works, watch my other video on that. So now, the basic principle of the bipolar PWM is that the gate signal S2 is the opposite of the gate signal S1. So it's 1 minus S1. So I'll just clear it up to get rid of what we don't need. So S2 is equal to 1 minus S1. And then we have that the output voltage is equal to the input voltage multiplied by S1 minus S2. And you can see now that if we insert for the gate signal S2 into the equation for the output voltage, we will get Vn is equal to 2S1 minus 1. And this is also what I've written here, as you see. Now we have a very simplified equation for the output voltage, but we're not done yet, because S1 is a binary signal, which is hard to control. So it's either 0 or 1. So instead, we want to have an average one. So we want to define a duty cycle, which is basically the average of the gate signal. So it's the average of S1. So we can insert this, then we get Vn, and then multiplied by 2 times the duty cycle minus 1. And now if we actually have a desired output voltage, we can solve for the duty cycle. So if we do that, you can say what we divide by, so this is V out. So we have, this is equal to V out. And then we can divide by Vn. And then we move over the 1, so it's plus 1. And then we divide all of this with 2. So this is the expression for the duty cycle. And now I've written this down here as well. So we have the duty cycle, here I call it D1, is 1/2 plus Vref over 2 Vn. So Vref is basically the desired output voltage that we want. And now this can be written as a block diagram. Now we have an equation for the duty cycle. So we have the output voltage that we want, and then we divide by 2 times the input voltage, and then we add 0.5. Then we get the duty cycle. And then we use a PWM to generate the gate signal S1. And then remember that this was the relationship between S1 and S2. So then we just use an inverter, or not, to get S2. And I will also show a numerical example where we use this. So in this example, we have a input voltage of 400 volts, and then a reference voltage, which is sinusoidal, with an amplitude of 400 volts as well. And then we have a switching frequency of 1 kilohertz, and then a carrier, which is triangular waveform. So this is just a fancy way of writing a triangular waveform with a frequency of the switching frequency. And then you can see here is the PWM. So here we calculate the duty cycle with the equation that we just derived. And then we use this is a PWM. So we get the gate signal, 1, and then we calculate the other gate signal. And then this is the inverter calculation. This is what the hardware does to get the output voltage. And then I added a moving average to get the average of the gate signals. So you can see that we have the reference voltage is in green here. It's the dashed line. And then we have the duty cycle is the orange here. And then here is also the carrier. So if we compare the carrier with the duty cycle, you can see that we get these two gate signals. And you can see that they are opposite. So when the duty cycle is larger than the carrier, we get, for S1, we get 1. But for S2, we get 0. And then when it's lower, it's the opposite. So you can see that these two gate signals here generate a voltage which goes between minus 400 and 400. And on average, this becomes a sinusoidal signal. So a bipolar PWM basically switches between minus 400 and 400. Now in my next video, I will show you how to implement this bipolar PWM in Simulink. And then if you're interested in this document where I go through, this is just a mini course where I go through 3 different PWM strategies for full-bridge inverter. So I also go through how a full-bridge inverter works and also how a PWM works. And then I compare these 3 strategies. So the next one I will make is the standard unipolar PWM. And I'll also make YouTube videos for these as well.